fellow of classical physics is photoelectric effect. First, observe that clean metal surfaces emitted electron called photoelectron when radiated with light. However, in classical physics theory, the kinetic energy of photoelectrons depends on light intensity. But that is not what they observe, okay? They observe that kinetic energy of photoelectron is actually depend on the wavelength of irradiated light, okay? So some of the observation that they saw in the experiment is low intensity light ejected electron too, okay? So it doesn't matter how much the intensity of light, as long as you get the correct wavelength, okay, you will see some photoelectron ejected from the metal surfaces. And the number of electron as measured as photocurrent depends on the light intensity, okay? So instead, the number of photoelectron actually depend on the light intensity. Kinetic energy, however, do not depend on light intensity, but depend on light wavelength. There exists a threshold frequency F naught, where if the frequency of light below F naught, no photoelectrons are emitted regardless of light intensity, okay? So the frequency of light need to be above some threshold, and then this threshold frequency F naught. Below that F naught, there will be no photoelectron, and then above that F naught, there will be some photoelectrons, okay? Different metal have different work function. Psi, where psi equals to H times F naught. H is just a Planck constant. F naught is just a threshold frequency. Einstein resolved this issue by assuming that light comes in quanta. Light itself is quantized, and he developed the equation Ke kinetic energy equals to Hf minus psi, okay? This equation is important in photoelectron spectroscopy test. So if you look at this diagram or figure, you will see that these metal surfaces have some electron. Okay, that's how metal conduct electricity, because they have free moving electron. And then you irradiate this metal surface by some light. Okay, but that light need to have frequency above the threshold frequency. Okay, so if you hit the metal surface with light above the threshold frequency, you will see some electrons called photoelectrons are emitted from the surfaces. And then you can calculate the kinetic energy of the photoelectron using this Ke equal to Hf minus psi. Okay, we have looked at some failures of classical physics, and then why classical physics theories cannot be used to explain those phenomena. This leads to the need for quantum theory, okay? The failures of classical physics lead to the need for quantum theory. There are three key ideas in quantum theory. The first one is quantized properties. What are the properties? The properties can be quantization of angular momentum, okay? Energy, spin, and so forth, okay? Second, probabilistic nature, okay? There is no such thing as exact deterministic in quantum theory. What you have is statistical or probabilistic, okay? It's all about probability. And then finally, wave particle duality. Wave particle duality, where you observe some entity behave like wave, and then some entity behave like particle, okay? Mathematically speaking, these three ideas actually come from the wave nature, okay? If you look at the math, the mathematics of wave, okay, you can use that mathematics of wave to describe all these three key ideas. The mathematics of quantum particle is described using mathematics of wave. Okay, this is some self-check quiz one. Okay, you can try to answer this self-check quiz, and then make sure you understand. Okay, this is a very typical questions that will come out in the test or quiz or even final exams. Okay, you answer this, then we can discuss in the class. Also, okay, self-check quiz 2. Okay, you can use those Einstein equation to calculate the energy of a photon wavelength. Okay, these are some conversion. Given work function, remember work function psi equals to h Planck constant multiplied by frequency. So you get this energy, and then you can determine whether this particular light, okay, with wavelength of 520 can emit photoelectrons or no. Okay. All this is about photoelectric effect. Okay, make sure you look at the photoelectric effect topic to answer this self-check quiz 2. Okay, here is kind of like a summary of key ideas or concept in quantum mechanics. Okay, the first one is quantized property. Quantization refers to discreteness instead of continuous. Okay, if you look at kind of like stairs, okay, tangga, okay, if you look at stairs, you will see if you have continuous kind of like a ramp, you can be on any point on this line. Okay, this is what we call continuous. If you look at stairs, stairs have discrete kind of like level. Okay, you can be here on the first stairs or second stairs, third, fourth, and so on. Okay, but never in between. Okay, if you ask me, okay, on which stairs that you step on, okay, I can only answer, okay, on the first stairs or second stair or third, but never like 2.3 stairs. It just doesn't make sense. Okay, some properties that can be quantized are energy. Okay, E equal to hf. This is what Max Planck figured out in black body radiation. Okay, the emitted energy from a black body is quantized. Second is momentum. This is what Niels Bohr figured out. Okay, mvr equals to nh bar. And then the third one is spin. Okay, you can either have a spin up or spin down for electrons. The second key idea is wave-particle duality. Particles are things like electron or even a carbon-60 molecule can behave like a wave. Okay, we will see that some example of wave. Okay, wave can diffract, interfere, or you can see like entity like photon, which is actually wave. Photon is just another name for light. Okay, can also behave like particle. Okay, this wave particle duality is related by de Broglie relation. Okay, so lambda, which is the wavelength characteristic of wave, equals to h Planck constant divided by p. P is actually a characteristic of particle. So you see, lambda wavelength characteristic of wave related to momentum p characteristic of a particle. Okay, so this is why you have this is where you have wave particle duality. And then finally, probabilistic or statistical nature. Okay, quantum theory forbid deterministic outcome, meaning that you cannot calculate precisely the outcome. Okay, what you get from the calculation is actually the probability. Okay, the outcomes are not exact but probabilities. It is related by Heisenberg uncertainty principle. So this is Heisenberg uncertainty principle. Okay, uncertainty in position x delta x. multiplied by uncertainty in momentum, delta P, must be greater or equal than h bar over 2. With particle duality, there are experiments to distinguish in which quantum object behave like particle or a wave. So particle behave like wave in electron diffraction or two-slit experiment, okay? Diffraction and interference are signatures of wave. So diffraction and interference, these are characteristic of wave. If you observe these two things, then you are so sure that it behaves like a wave, okay? So this is the electron diffraction. On the right is, on the left is X-ray diffraction passing through aluminum foil. On the right is electron diffraction. One is X-ray diffraction, one is electron diffraction. And then if you look at this figure, you have two slit, two opening, and then wave pass through this thing. They will interfere with each other and produce interference pattern on the screen. Okay, then when wave behave like particle, wave behave like a particle in photoelectric effect and in Compton scattering. We have seen about photoelectric effect where light hit a metal surface and eject the electron. Einstein assumed that the light must be a particle, okay, a quantum of energy. Now, Compton scattering, if you have some sort of incident photon, X-ray or gamma ray, and then it hit this electron, and then they behave like a billiard ball, okay? If you play snooker or pool, you know that all those things must be kind of like particle, okay? So this is what we call Compton scattering. Two-slit experiment, okay, interference pattern in a two-slit experiment is a characteristic of wave nature. Anything that display an interference pattern is a wave. Experiment with electron, protons, even buckyball, C60 molecule, also show the same interference pattern in two-slit experiment. It means that this particle behave like a wave. So I put a link to a YouTube video. You can watch this thing, okay? It's about two-slit experiment. And then you can try to answer this very short quiz, okay? What happens if you shoot through two-slit a baseball or a marble or nanoparticle? Do you expect to see interference pattern or no? So I hope you can answer this at home. And then finally, probabilistic nature. Probabilistic nature arises because of wave character, okay? Quantum theory does not give exact outcome, but probabilities. Determinism is gone in quantum theory, meaning that you don't get exact outcome, okay? The exact outcome is what we call determinism. So in quantum theory, determinism is gone. No more determinism, okay? This probabilistic nature is encoded into Heisenberg uncertainty principle, which states that it is impossible to measure both position and momentum of a particle at the same time or simultaneously precisely. Once you get exact position, you lose information about momentum or vice versa. You get precise information about momentum, you lose information about position, okay? And then there is another rule called Bond's rule, which states that the modulus square of a wave function tells a probability of locating a particle. We will look at more about Bond's rule in the next lecture when we deal with Schrodinger equation and how to solve that Schrodinger equation to get a wave function. Okay. So far the momentum P and characteristic of particle and the wavelength lambda characteristic of wave is related by de Broglie relationship. Okay, if you look at this well-defined wavelength, you can see the wavelength. Okay, you will have a poor momentum, and then if you look at well-defined momentum, you will have poor wavelength.